Welcome to the second WEB.BM instructional video, which will teach you how to create scenarios for your projects. Before you do that, you have to understand the concept of priority factors and operating zones. When we create scenarios, we also have to understand node policy groups and node zones, as well as channel policy groups and channel zones. Those are explained in the following slide, where you have a small example with one reservoir, one tributary, one irrigation block, one municipal demand, and one downstream channel which has environmental flow targets. Each of these components is shown in the diagram below, and each of them is split into two or more zones. For example, reservoir storage is split into three zones at around 60% of storage and 20% of storage, while irrigation and municipal zones are split into 100% and 50%. The natural channel flow zones are distinguished as ideal and minimum. You will see that each zone has a certain number assigned to it, which is identified here as a cost priority factor. When we have reduction in supply, you will notice the first component that would have its water supply reduced would be the ideal zone of the natural channel. How would this be visible? Well, simply the runoff that is coming from the tributary would be diverted to irrigation and to the municipal component, thus reducing the flow in the most downstream channel. This is a logical selection by the model because this particular zone has the lowest penalty, and if we bring the flow to it to zero, that will minimally change the value of the objective function. All other zones will have their flows full and they will be multiplied by their respective factors. The next lowest priority factor in this system is the top storage zone. What the model will decide to do in case of increasing shortages is to sacrifice the storage at the expense of maintaining irrigation supply at 100% and also municipal supply at 100%, as well as the minimum biological requirement at the downstream channel. So the storage may be used for one of those three purposes. Further reduction in storage, though, will cause managers to call for some reducing the water use. So the first reduction will be to the irrigation component. It will go down to 50% of its demand. The next reduction will be to the municipal supply, because these are penalties of 20 and 30, which are the next lowest penalties. Once this happens, we're going to have additional support from storage to maintain the 50% water use for irrigation and for municipal supply and the biological minimum in the natural channel downstream. Only after we have reached the bottom of the second storage zone shall the irrigation supply be completely shut off, as well as the municipal supply, and if there are further drought conditions, we will not be able to maintain the minimum flows. Now, you need to notice a few things. If you multiply all these weight factors or priority factors with the same number, or if you divide them with the same number, as long as their relative difference between them remains the same, they would produce the same flow solution. If you, for example, change the priority factor in the second zone of the reservoir from 40 to 41, you will still get the same flow solution. So there is more than one set of cost factors that can deliver the same solution. Also note that these zone bounds are changing over time. What you see here is only one time step. There is 100% of the demand, but that demand changes from one time step to another. So may the minimum flow, and so may the size of each of the reservoir zones, even the definition of the zones being full. In fact, if you look at the reservoir zones, they typically look something like this. So they are varying from one time step to another throughout the year. What we have in this case is ability to use multiple time step solutions, which introduces some science into how these zones can be created. When you solve the model using multiple time step solutions, you are allowing the model to play with the entire live storage zone, knowing that live storage may actually be changeable over time. As you can see here, there is some drawdown for increasing the flood storage during the periods when floods are very likely to happen. Also, at the end of the dry season, sometimes there is a requirement to maintain certain minimum with some storage still in the reservoir to just act as insurance in case the onset of the monsoon season is late. Normally, you would be able to model the whole reservoir operation using multiple time step approach with only 3 zones. In this case, it's dead storage zone, conservation zone, and flood storage zone. However, this may have some implications on your calculation of net evaporation. As you can see here, the blue line represents the area versus volume curve based on the data for the Barge reservoir, while the orange line represents the same curve which was plotted only with these points that we identified here: dead storage zone, full supply level, and the maximum elevation. And you can see that for simulated levels that are somewhere in the middle of the live storage, we have a significant discrepancy between the actual curve and the curve that the model recognizes based on only these 4 points that were given to it. So we may have to introduce some additional zones in the live storage zone to simply better represent this curve and to make sure that the evaporation is calculated properly. How do we use the multiple time step solutions to create better zones? Well, we look at every solution as a perfect rule curve for every year. So these are now model outputs. We can analyze them statistically, create these probability density functions for the end of every time step, and then connect the levels at the end of every time step which have the same probability of occurrence, thus creating these comfort zones where the reservoirs are most likely to be within dry years or wet years or median year. In the end, don't forget that what we are doing in scenarios is we are specifying these priority factors, which are important because they determine how the system should be operated. And we are also specifying these upper bounds for each zone in case we are deciding to have more than one zone to represent a particular water use. We are now ready to continue with the work we've done in the previous video where we set up a project. But we have to add the scenario to this project. So log into your system and click on the Barge Reservoir System project in the project list form. You will see this button scenario that will show up underneath the project list. Click on the scenario and it will show you the list of existing scenarios for the selected project. In this particular case, we haven't created any scenario yet, so the list is empty. We're going to click on the Add button, and now we're going to enter the information such as the name of the project. We will select the monthly time step here. The calculation will begin on July the 1st of 2008 and it'll end on July the 1st of 2009, same as in the project, although it can be any date within the project. Scenario type, which refers to the calculation type, will be in this case selected as multiple time step optimization year by year. The other options are multiple time step optimization for all years or single time step optimization. We will be dealing more with these options in another video, but so far select MTO year by year. These are going to be steady state calculations. The other option is sour channel routing, but the sour channel routing option is only available for daily time steps or time steps that are shorter than a day. And these two options, number of iterations and travel time tolerance, are also associated with the sour channel option. Note that you can print the results of this scenario either in the units of volume or in the units of flow. The default is the units of flow. Save changes. Now that we have a scenario, we need to create policy groups for both nodes and channels, and we need to make sure that each and every one of our components that is in the project is in one of the policy groups. Let's start with nodes. Our policy group for nodes is empty, of course. We're going to add one policy group here. We're going to call this policy group reservoirs. The node type here obviously is going to be reservoir. We are now going to be specifying how many zones above the target and how many zones below the target we want to include. And there is this default for the offset factor, which we'll explain later. At this point, you can just enter 0. Equal deficit constraint refers to irrigation components only, so we will not be entering anything related to reservoirs. So we've just created a policy group for reservoirs. And now on the right hand side, there will be a list of all reservoirs in the project. In this case, there's only one reservoir. And, we want to include it in the policy group, so we're going to click on the checkbox here. The next, we're going to add policy called irrigation. It will be consumptive use with only one zone below. We don't need the offset parameter. Equal deficit sharing for all components within the group from time step 1 to time step 12. So now we have two groups. One is the reservoir with only one component, and the other group is the irrigation group, which has two components. We are now creating the channel policy groups. So again, click on the scenario button, select channel policy groups from the scenario. This list is empty. We are going to start adding policy groups. First, we can create irrigation canals. These are going to be channels of type diversion. They have no zones above or below, and we don't need to use this offset variable, so we're just going to click on Save Changes. Immediately we see two diversion canals that have been identified in the project, and we're given a choice to include them. We will include them in this scenario group, in this policy group, by simply clicking on them. The next policy group is a channel that we can call inflow river. This is a river reach. It's going to have 0 zones above and 0 zones below the ideal. River reaches always have one ideal zone by default. And the simplest case is to have no zones above or below the ideal. Save changes. And we're going to include one channel in this, and that will be Bargy inflow channel. That will be channel in this policy. Then we are going to have Bargy spill channel. It is also river reach, and this time it's going to have one zone above the ideal and no zones below the ideal. We're going to click on Save Changes. There is going to be another river reach called Bargy Hydro, which represents the hydropower plant. This river reach will have no zones above and no zones below. And finally, one more, which we'll call Bargy outflow. It will have one zone below the ideal, 0 zones above, and one zone below the ideal. Because this is an environmental flow channel, it needs to have a zone below the ideal, which will have some kind of weight factor or priority factor. Save changes. Now we need to make sure that we populate Bargy spill is going to have Bargy spillway. Bargy outflow is going to have Narmada River, which is the most downstream river. Bargy hydro is going to have Bargy hydropower. So each policy group has some channels, and none of these channels overlap. In other words, one channel cannot be in two policy groups, and the model has a check to make sure that's the case. So going back to our node zones now. When you click on node zones, you see two groups. Could have been more groups here, but we only have two node groups, and each group will have its members listed and also its zones in the lower part of the form. Enter the information that we have prepared for these weights. Specify the importance of being in each zone. We are asked to basically paste 5 numbers here because there's one zone above and 4 zones below. Paste 5 numbers from Excel or any other program from where we copied them from. First time, pasting will be required. When we save, after we save, we will be able to edit these entries by simply clicking on this line and clicking on the edit button. But for the time being, for the very first time, we have to use the paste command. We also have to specify the starting level for Bargy Reservoir, and that level is 408.65 meters. We need to save this initial elevation. We'll get the message that it's saved. And now we are being asked to specify the zone bounds. Note that we require a year, Julian day, which is the day between 1 and 365 within a year, and then zone bounds. And we can basically have them specified for multiple days such that we can provide all sorts of shapes for the zones. Here we're going to again prepare this information in spreadsheet and paste from clipboard. After we do that, we need to click on the Save button. You should notice here that simulation starts on day 183. This is July 1st, counted from January 1st, for the year 2008, which is a leap year. If it weren't a leap year, this would have been, July 1st would have been day 182, as it is for year 2009, which is not a leap year. If we do multiple year simulation, this is still sufficient. It'll be copied from year to year. However, this entry form allows us to have different zone bounds for every simulated year, if we choose to do so. Going back to irrigation, we are going to specify that there is only one zone, and we need to specify the weight factor for that zone. And it's going to be a weight factor of 30. So we have to copy number 30 from the spreadsheet and save. Click on Save All. Similarly, for node zone levels, this is now a very easy entry. We only have one zone, and that zone is 100% of the demand. So in this case, we're going to be putting in number 1 and clicking on Save. If we had two zones and the first one was 20% of the demand and the second one was 80% of demand, then we would have 1 and 0.8 pasted here on a single line. Keep in mind that when we specified node zone weight, that weight is the same for both irrigation blocks. However, the zone bounds may be different, so we have to specify a unique zone bound for every block. In this particular case, we have to simply paste number 1 again. Click on Save All, and this ends creation of our zones for the components of type node, which are reservoirs and irrigation. We can go back now and click on the channel zones. In this particular case, we are asked to enter zone bounds for irrigation canals. Irrigation canals have a priority factor of 0. They simply are used for conveyance. So here we're going to paste 3 numbers, year, which will be 2008, Julian day 183, because that's the time when the simulation starts. Although if you specify day number 1, it should still work because it will cover the entire year, and the ideal zone. If we specify it like this, with only one line, then the zone level for 1000 cubic meters per second will never change. It will remain the same for all simulated time steps. And we need to repeat the same. Click on Save every time you enter information. Now for channel zones for other components, we have similar information here, but river reaches have a much higher flow capacity. Enter 0 because for natural channels, and click on Save. For zone levels, we can use something that will never be exceeded for the inflow channel into Bargy, that is, for example, a flow of 9,000 cubic meters per second. The highest ever recorded was above. Now we're looking at Bargy spill. It'll have similar information, but now we have 2 zones, and the zone above the ideal is going to be very unfavorable to be in. In other words, we don't want to spill. So that zone will have a high penalty for being in it. And we're going to click on Save. This penalty should be understood as exceeding the ideal zone, which means that it is used with a negative sign internally in the model. Our zone bounds are going to be top zone being 9,000 cubic meters per second as before, and there is going to be an undesirable factor or cost of 1,000 units per cubic meter for being in this zone, which means the spills are going to cost us a lot of money. This channel will have an ideal zone with a zero thickness. The ideal zone will have the upper bound of 0 and lower bound of 0, so there will never be any flow through the ideal zone. Next is Bargy hydropower, which is going to have maximum flow capacity of 218. I'm going to click save and then change 9,000 into 218 by using the edit option. 218 update. Again, this is an ideal zone which should have a zero penalty, so we're going to enter it here. And finally, Bargy outflow, which has two zones. It will be very undesirable to violate the minimum environmental flow targets. That's the meaning of this priority factor of 5,000. So we need to specify the zone bounds, and now they'll be given for more than one point in time. So when we paste on the clipboard, we're going to paste information that looks like this. From day 183, which is July 1st, to day 214, we're going to have 100 cubic meters per second. From 214 to 245, which is only 1 month, and that is the month of August, the flow requirement is going to be 155 cubic meters per second, and then after the month of August, for all other months, it will remain at 100 cubic meters per second. Click on save, and this finalizes all our components. We just need to go through them again and make sure that each and every one has both the priority factor and zone bounds specified. Here are a few final reminders you have to take home with you. First of all, how does the model interpret reservoir zones? Reservoir zones are target levels, and you specify them in input data forms by giving various changes in the target level for various points in time. So here we only have, say, 1, 2, 3, 4, 5 points that cover the entire year. Now, when the model starts to run, it has to develop a target level for every simulated time step. So how does it do that? It simply reads from these lines for every zone the elevation at the end of the time step. If you want to ensure that these points, which were critical, are indeed met, they have to coincide with the end of the time steps. If they don't, the following will happen. The model will interpret these lines to look like this internally. So be careful about this and make sure that your zones are specified such that they hit the end of the simulated time step. The way the model interprets channel zones is a bit different. Channel zones are given as constant values which remain constant until the next point in time comes with a different value. If you, for example, look at this zone number 1, here is the first value. It will be around 2,000 for the top zone. For the same first time step, which is first point in time, which is a 0 coordinate here, you would see something above 1,400 and then 1,100 and then just above. They would remain unchanged until the second time T2, which is around day 135. And all the readings will be the same for all time steps until we come to this time step where we have a breakdown. 135 is not the end of the week. So if it happens that you have a simulated week or a time step which has this break in between, then the zone targets will be adjusted to correspond to the weighted average of the two values that you see here. Finally, consumptive use zones are given as percentages of consumptive use. So in this particular case, you see 4 zones. The first zone is the dark segment here. It's only 10% of the demand. The second zone, again, is also 10% difference between 90 and 80% of the demand. Third zone is 15% of the total demand. And the fourth zone is 65% of the total demand. This essentially represents a rationing policy of some sort. These demands are given as a time series or use files given for every consumptive use nodes. So all we need to specify for zones are the weight factors and the zone bounds, which are really given as fractions. Finally, the offset variable is the one that we were mentioning a couple of times. It's shown here as 0.01. Keep in mind that we're giving the weight factors only for the first component in the list. Let that be channel A. Channel A has weight factor 1, 2, 3, and 4. That could be this channel net 052. When we're given a zone weight offset as something that is non-zero, other channels will have their weight factors calculated using the following formula. What this does is it makes sure that there is a unique value for each weight factor in each operating zone. And this is a good idea because if you have too many zones with the same weight factors, the model may be developing different solutions that have the same value of the objective function. In other words, you're creating a situation where there's more than one optimal solution. This is also a shorthand or efficient way of entering data because if you look at, for example, this group of 5 natural channels, this could have been consumptive use or reservoirs, the same rule applies. And we have 4 zones for each, that's a total of 20 weight factors. In this way, we're only entering 4 of them plus 1 weight factor, and we're recalculating internally 20 numbers. Thank you for watching. We came to the end of our instructional video on scenarios.